We're getting ready to get into our first type of circuit analysis. Now, this isn't the pure circuit analysis because ultimately what we're going to be looking at are circuits that just have capacitors. And so ultimately they're going to be circuits where current isn't flowing, okay? Because you know that once capacitors are charged, current stops flowing, right? But we're going to look at this, and the cool thing is, even though this isn't this isn't a situation where we have current flow, the type of things we look at and how we break things down with capacitors are actually going to go over with us when we start looking at circuits that have resistors. And so we're going to start learning some important skills of circuit analysis through this process. So what I want to start out with is I want to talk about what's called the equivalent capacitance for capacitors that are in series with one another. Okay, so let me bring up the picture of my battery, and this time I have two capacitors. Okay, and what I'm going to do is I'm going to connect those capacitors to the battery. The top plate of capacitor 1 is attached to the positive terminal of the battery, and the bottom plate of capacitor 2 is attached to the negative terminal of the battery. And then and these are wires, and then what I do is I connect the bottom plate of capacitor 1 over to the bottom plate of capacitor 2. Now, these two elements, these two capacitors, are what we would say that they are in series with one another. And the way I think of what defines a series connection, okay, is that two elements in a circuit are in series if no branching occurs between them, okay? Now, what do I mean by branching? Well, this is a fairly simple circuit, right? If it was more complex, it might be the case that as you come down here from capacitor 1 to capacitor 2, there's actually another wire running off this direction, another path, and this is connected out here to some other part of the circuit. This is what we would call a branch point, okay? This connection here is a node, and what we have here is branching in our circuit, okay? If there's something here running out that's connected to other stuff, capacitor 1 and capacitor 2 are no longer in series, okay? They're only in series if there is no branching between the two capacitors. Now here's the question that we want to ask, and I'll define some of this, but if you have two capacitors in series, what then is the overall capacitance of the circuit? You know, we call that the equivalent capacitance, or you'll hear me say sometimes the total capacitance of the circuit, okay? So we don't expect necessarily that this situation is going to be, you know, just like the prior situation. You know, there's going to be, these two capacitors are somehow going to interact to create an effective capacitance for the circuit, and we want to know what that is. Well, the way I like to get this conversation started is I want you to think about this from the perspective of the battery. I want you to imagine that you come to class next time and I have a shrink ray, okay? And I shrink you down and I put you inside of my battery because there's a control room in there where you are able to monitor the flow of charge as it goes out of the battery. Now, you don't know what's out here. You can't see the outside. You're inside the battery, and you can just tell if charge is leaving or coming in or what's going on there, okay? Now, think about what's going to happen. Even though we don't know exactly what the outcome is going to be yet, you still can understand and would expect that as charge starts to flow out of the positive terminal on the batteries, that eventually the capacitors are going to become fully charged, right? And charge is going to stop flowing out of the battery. Now, here's the thing. You're inside the battery. You don't know there's two capacitors out here. You just know that charge was moving out of the battery, and then at some point later, it just stopped flowing. So from your perspective, that's exactly what happens with a single capacitor. Your most practical guess would be, oh, there's just one capacitor out there because, hey, the charge started flowing and then it stopped. That's what a capacitor does. So from the perspective, your perspective, the perspective of the battery inside it, it's like there's just one capacitor out there, right? And it's that capacitance. You could measure how much charge flowed out of your battery, right? You know what the potential difference is across your battery. And you could actually figure out what the capacitance has to be, because remember, the total charge is equal to the capacitance times the potential difference across the capacitor. And you know that the potential difference across a capacitor is going to be equal to the potential difference across the battery when it's charged, All right, so that's what we mean by equivalent capacitance. It's the capacitance that you would say is in a single capacitor that would make the circuit behave in exactly the same way as it does with the two capacitors. Okay, so that may be a little silly, but what I want you to understand is this: for all practical purposes, the charge is going to act like there's a single capacitor out there. And we would like to know, well, then what's the value of that capacitor? And that's going to be the equivalent capacitance of these two things together. Okay, and so we could use Q total as it's just equal to the equivalent capacitance times the potential across the battery. All right, now let's think about what's going to go on here, because physically I want us to, not just jump into equations, but think practically and physically what's going to go on. Now you know that the moment I connect this circuit, positive charge is going to start to flow out this line right here, go down this branch, all right? And it's going to start depositing on this plate. And so we're eventually going to get an excess of negative charge on capacitor 1, right? And we'll just say there's a total amount of charge. And of course, that total amount of charge that deposits up there is how much you as the little microscopic person inside measured going out of the battery, right? So that's all on this plate. But now let's think electrically about what that's going to do. We have an excess of positive charge up here. How's that going to affect the charge status of the lower plate? Well, now this looks really wide. Remember, these two plates are really close together, okay? But all this positive charge up here, it's going to push away positive charge that's in here, okay, on the plate down here. And what that's going to do is, and let me make sure I'm being clear here. It's going to push that charge away because, look, positive is going to push away positive, all right? Or we could also say positive is going to draw in negative charges because of the nature of electric forces, right? And so what's going to happen is on this bottom plate, we're going to get an excess of negative charge, right? That's going to be equal in magnitude to the amount of charge that's on the positive plate. So in other words, we get Q total that came out of the battery up here, but what that does is it induces an equal amount of negative charge on this plate, right? Well, okay, so this positive charge or negative charge gets pulled in, or however you want to think of it, the positive charge gets pushed out. Well, where's that positive charge going to show up at that's been pushed off this plate effectively? Well, it's going to travel down this wire and it's going to deposit down here on this plate, right? And so what we're going to get down here on this plate is an amount of positive charge that's going to be equal to the amount of positive charge that was on this plate up here. Again, this is all electrical forces, induced charges, and think of it this way: if this positive charge pulled the electrons in, which is practically what's going to happen, it's electrons that are moving. So this positive charge is pulling excess negative charge up here to the plate to balance it out. That's going to leave an excess of positive charge down here. Well, what's that going to do? The battery here sending out negative charge, and we know the amount of negative charge that it sends out has got to be equal to the amount of positive charge it sent out. And so we're going to get, again, an equal amount of negative charge on this plate as we had on this plate up here at capacitor 1. Okay? And so physically, that's what's going to go on. But what I want you to see is that in terms of magnitude, both plates are going to have the same amount of charge on their plates. And that charge is the charge that ultimately came out of this battery. Okay? And it can, let's think about that for just a minute. Now, let's think about the voltage drop. Okay? Let's talk about the voltage across capacitor 1. Well, using that relationship, Q is equal to C times delta V, we can calculate the voltage drop because we know C and we know the charge, right? So the voltage drop across capacitor 1 is just going to be Q total divided by the capacitance of capacitor 1, right? And similarly, we can come down here and do the same thing for capacitor 2, all right? And we're going to find that the potential across capacitor 2 is just the total charge on that capacitor divided by its capacitance, right? That's what we're going to get there. And so we can actually calculate the potential drop now because we know how much charge had to be deposited on these plates, and we know the capacitances. Okay, so we've found the potential drop across both. Now, remember, don't forget what our goal is here. We're trying to figure out the equivalent capacitance. In other words, what capacitance do C1 and C2 combine together to give that is the effective capacitance of the circuit, okay? Well, now let's think about this because we're going to have to think about potential. As I go from one side of my battery all the way around to the other side of my battery, the potential has to drop the same amount of the potential across the battery. In other words, say the battery is a 9-volt battery. And so we have the top up here at 9 volts. We got the bottom at 0 volts, all right? So as we go around the circuit, our potential has to drop all the way down to 0. It's got to go from 9 to 0. Now, here's something that's really cool about circuits. I told you we're going to learn some basic stuff about circuits in general. And that is that these wires that are in circuits are really good conductors, right? And what you get is that the potential doesn't really drop until around here because the potential drop is due to the collision of the moving charged particles with atoms in the material, okay? Well, that's the thing about a conductor. They just don't oppose. There's not a lot of collisions, right? And so you get no really drop in potential. Where the drop is going to occur is across your capacitor, all right? So I'm going to have to go from here, and I'm going to drop by an amount, delta V1. And then I'm going to come down here, and I'm not going to drop really again until I get here to the second capacitor, and I'm going to drop by delta V2, right? Well, we said that the total amount of drop around a circuit has got to be equal to the potential provided by the battery. And if all the drop is occurring across my capacitors, that means that if I add up the potential across V1 and the potential across V2, then they've got to be equal to the total potential of my battery. And so that's the key. As you move around the circuit from the positive to the negative terminal, the voltage has to drop a total that's equal to the potential of the battery. All right? In other words, if we add delta V1 and delta V2, they're just going to be equal to the potential of my battery, right? Well, here's where we're going to be able to get back to capacitance now. Because delta V of the battery, if we go down here to the equation, isn't that just going to be the total charge divided by the equivalent capacitance, the combined effect of these two capacitors? Yeah. And delta V1, we've got an expression for that. And delta V2, we've got an expression for that. And so if I put those in, then I get this. This is just delta V battery is the total charge that left the battery divided by the equivalent or total capacitance. You know, delta V1 is the charge on capacitor 1 divided by its capacitance, and delta V2 is the charge on it divided by its capacitance. But what's handy here is the fact that we know that the total charge has to be the same. So I can divide out my total charge, get rid of them, and so what I get is this, is that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. And so if I wanted to solve for C equivalent, I take the inverse of both sides, and what I get is that my equivalent capacitance is just equal to 1 over C1 plus 1 over C2 to the negative first power. In other words, I have to do this math and then take the inverse of that to get my equivalent capacitance, okay? And we can generalize this. We did this for 2 capacitors, but if I had 100 capacitors that were in series with each other, then what I would get is that the equivalent capacitance of any number of capacitors in series with one another is just given by this equation here. You take 1 over C1 plus 1 over C2 plus 1 over C3 all the way up to 1 over Cn, add all that together, and then take the inverse of that. Do 1 over all of that, okay? Don't forget this. Students forget this all the time. They'll do this, and then they'll fail to do this part, all right? But what this does is this will tell us, okay, remember, from our perspective here in the battery, it looks like there's just one capacitor out here, and that capacitor would have a capacitance that we could measure using what we know internally from the battery, but it's the result of these two combined. And how do the two capacitors in series combine with one another? They combine like this, okay? Well, let's just look at an example. Let's say we have a 9-volt battery that's connected in series with 3 capacitors. One is 3 microfarads, one's 4 microfarads, and the other is 5 microfarads. And I want to know how much charges are going to be on each of the plates after the capacitor is fully charged. Okay? Well, let's think about this. Here's a picture. I've got my 9-volt battery. That means delta V, the potential across the battery, is 9 volts. And I've got my 3 capacitors in series with one another. No branching here, no branching here. So these 3 things are in series. Okay, well, let's figure out the total amount of charge that's going to come out of the battery. Well, we know that the total amount of charge is just going to be equal to the equivalent capacitance of those 3 things combined multiplied by the potential across the battery, right? Well, we need the equivalent capacitance. Well, there's our equation. The equivalent capacitance is just this, to the minus 1. And so I just put my values in. Now, I don't have to convert this over to farads right now. I can leave it in microfarads for this part. And so what I get is that my equivalent capacitance is going to be 1 over 3 plus 1 over 4 plus 1 over 5. I'm going to do that, and then I'm going to take all that to the minus 1. And when I do that, what I get is 1.28 microfarads. It's micro because the units I had in here were micro, okay? So 1.28 microfarads of capacitance. In other words, I could get rid of all 3 of these capacitors and just put one capacitor in here that has a capacitance of 1.28 microfarads, and it's going to make this circuit behave exactly the same way. The same amount of charge is going to come out of the battery. Okay, well, now that we know the equivalent capacitance, we can find the total charge. Here's our equation for doing that. So the total charge is going to equal the capacitance. Now notice what I had to do here. I do need to be in farads when I do my calculations. So I took this 1.28 microfarads is 1.28 times 10 to the minus 6 farads. That's my micro piece right there. And then I've got 9 volts, and so do the math, and I get 1.156 times 10 to the negative 5th coulombs, which is 11.5 microcoulombs, okay? So that's what you do with capacitors that are in series with one another. Remember, our goal is to say, okay, what's the overall capacitance that they create together? And this is how we figure it out. That's our key, all right? And so anytime we have series, a group of capacitors in series, we can reduce them down to a single capacitor that has their combined capacitance, okay? So, so there's an example of that. This is how we handle capacitors in series, and you know, need to know how to do this.